So today we're going to cover trigonometric substitution. I would say personally, I feel like this is one of the hardest sections from the trig or the integration techniques that we're learning in this class. So this one you got to really hold on for. This one's a little bit rougher. I'm going to give you guys some substitutions, some ways to think about things, and you'll start noticing some patterns. But so suppose let's just, or I should say, let's do some review of trig first, just to make sure we're all on the same page. So if we say that secant of theta is worth x over 3, then I'd like to be able to find the sine and the tangent, just to see if I can. So what I'm going to do first is I'm going to say, well, secant theta equals x over 3. But you guys know that the secant is worth what? So remember that secant is 1 over cosine, right? So cosine would be adjacent over hypotenuse, but because it's the secant, then it's going to be hypotenuse over adjacent. So this is hypotenuse over adjacent. Okay, so let's kind of draw our triangle. Let me draw this a little better. Okay, so this is our theta. Now, if this is our theta, then we know that the hypotenuse side is x. So right there, let me do it in red. We know that's x, and we know the adjacent side is 3. Well, remember, a squared plus b squared equals c squared. So then you know that this side is the square root of what? X squared minus 9. All I did was a squared plus b squared equals c squared. And I just solved for the missing side. So this would be x squared minus 9 square rooted. Okay, so we have this triangle now. So that means given this information, given this information, I can now find the sine of theta. So the sine of theta would be opposite over hypotenuse. So the opposite side is square root x squared minus 9 over hypotenuse, which is x. And if I wanted to know the tangent of theta, tangent we know is SOHCAHTOA, opposite over adjacent. So the opposite would be x squared minus 9 over the adjacent, which would be 3. And again, we're going to need to build these triangles for this problem, okay, or for the problems in this section. So this will be the idea behind it, all right? So let's go over here. Let's look at this particular problem. So, and again, later on in, I think it is 8.5 or 7.5 or 7.6, depending on the book you're using, we're going to kind of talk about how you decide when to use trig sub. Okay, so suppose we're given this x squared over square root of x squared minus 9. So I'll kind of give you guys a rundown of it, but basically it's going to kind of it's going to be up to you to decide what technique. Are you supposed to use, completing the square, or are you supposed to split it, or are you supposed to use u sub? Now you guys have trig integration. You guys also have integration by parts. Now we're learning trig substitution. In the next section, we're going to learn partial fraction decomposition. So you guys are going to be learning all these techniques. And one of the hardest things to do is to decide which technique is most appropriate for this problem. And again, that's the thing about this section, this chapter, is it's not a lot of, it's theory per se, or I guess concept, but it's really a heavy dose of mechanics in this chapter, okay? So we have dx over the x squared, square root of x squared minus 9, and we want to integrate this. So you guys are going to have to trust me on this real quick. So I'm going to make a substitution. I'm going to say that x equals 3 secant theta, okay? So I'm just going to say this is from now on, for this particular problem, x is worth 3 secant theta, okay? Well, if x is worth 3 secant theta, then I need to find a way to write dx in terms of theta. So then I'm going to find dx is worth, now the derivative of 3 secant theta, and again, we're just doing what we always do in all of these problems, ddx, but in this case, we're going to get dx is equal to, let's see here, 3 what would that be? Secant tan, secant theta, tan theta, d theta. Now, technically, it's d theta over dx, but I moved the dx over to the other side. That way, we can have dx is equal to this. So we have 3 secant theta tan theta, okay? And if you're wondering where the d theta over dx would come from, remember, you are taking the derivative with respect to x of a theta. So we're going to have to use the chain rule on that, all right? So this guy, when you differentiated that, became d theta over dx, and then I moved the dx over. So, but we've done this many times in U substitution. So the thinking is similar. Okay, so now we have, I'm going to erase this since you guys know where everything came from now. So now we have dx is equal to 3 secant theta tan theta d theta. Okay, so that looks kind of rough, but that's what the substitution would be. So I'm going to come over here and I'm going to draw my triangle. And that's theta, right? And we know that because x is equal to 3 secant theta, we know that x over 3 is equal to secant theta. So kind of using the thinking from the last problem where we were just reviewing trig. So that means that this side, the hypotenuse will be x. This will be the square root of x squared minus 9, and this will be 3. Okay. So this is the triangle that we've just built based on theta, right? And based on this rule that we made up, all right? So now we're going to plug in what we know. So we know that dx is worth 3 secant theta tan theta d theta. Now, once again, you guys, where did I get this from? I got that from right here. This dx is worth this, right? Because I said that a dx is worth 3 secant theta tan theta d theta. Well, here's a dx right there, right? So that's what it's worth. Now we're going to divide that by x squared. But what did I say x was? I said x was 3 secant theta right here, right? So then that means that this is going to be 9 secant squared theta times the square root. And then I said x, so this would be 9 secant squared theta minus 9. Now we got to start cleaning up. So let's see here. This guy is a 1, and this guy's a 3, because this is pure multiplication, so that's legal to do. So this will become secant theta tan theta d theta divided by secant squared theta. Oops, let me put a 1/3 out here. So I pulled this 3, you guys, and I pulled it out front, okay? Now we have the square root. Now I'm going to factor out the 9, and that's going to become 9 times secant squared theta minus 1. All right, let's do some more cleanup. This will become 1/3 secant. You know what we could also do? We could also cancel this secant theta with one of those secant thetas. Just, again, we're just trying to clean. So this will become tan theta d theta all over secant theta, because we canceled the square of it. And then, oops, and then this is actually 3. Now remember, secant squared theta. So I showed you guys that if you had, let me write a little scratch work here. I showed you guys that if you had sine squared theta plus cosine squared theta equals 1, you could actually, if you divided everything by cosine squared, you would actually get, you'd actually get tan squared theta plus 1 equals secant squared theta. Now remember, we have tan squared theta. I'm going to move the 1 over, so I have secant squared theta minus 1. This right here is the same as when I factor this. This is going to become 9 times, now look, secant squared theta is worth a tan squared. So this will become 9 times tan squared theta. Now you may not think that that's important, but now it's a multiplication problem. It is no longer addition, subtraction, and they're perfect squares. So we now have 1/3 integral tan theta over, let's see here, secant theta. Now what's the square root of 9 is times 3. The square root of tan squared is tan theta d theta. Now we can do some more canceling. Our tangent cancels with this tangent. Let's keep going. So now we have, oops, this will be 1/9 now, right? And this will be d theta over secant theta, okay? Now here's the thing, a secant theta in the denominator is the same as a cosine theta in the numerator. So if I clean this up, this just becomes cosine theta d theta, which just becomes 1/9 sine theta plus c. That's a lot. You guys, hopefully you notice that's a lot. There's a few little things, like you could have probably gone straight from this to probably this, but sometimes it's hard to make those jumps in your head. So we have 1/9 sine theta plus c. That's not actually the right answer because nobody ever asked us for theta. They wanted to know in terms of x. If we look back to the original problem, it's this, right? X and, you know, dx. So we got to back substitute everything. So now we're going to get 1/9 sine. Now what was theta? Oops, I'm sorry. I did it wrong. We have to think, what is the sine of theta worth? Well, we go back to the triangle that we built. If this is theta, what's its sine? Well, sine of theta would be opposite over hypotenuse, square root x squared minus 9 over x. So that's what I write. 1/9 times square root x squared minus 9 over x plus c. And that would be our final answer, because the sine of theta is worth that if theta is built from this triangle, okay? Or this triangle is built from that theta, I should say. That's a better way to say it. So as you guys can see, not an easy problem. Look at this. This is definitely tough. And part of the reason is it's also hard to see. You guys notice that you started with this, right? This doesn't look very bad. This doesn't look like some terrible problem, but it turns out you got to do a lot of work to get there. We made it look like this. Look how terrible we made this problem. Look at this. This is a terrible looking problem. This, to me, looks easier than this problem. But because I know a lot of trig identities and I know how to manipulate my trig, I could turn it into, so notice this problem, after all the cleaning, turned into this. Look at this. Look how easy that problem is. Which would you rather integrate? This guy or this guy, right? It's no comparison. So just keep in mind that even though it doesn't look like you're getting anywhere, you actually are making the problem much more simplistic for yourself, okay? All right, so let's look at another one, okay? So the question would become, I have a lot of students that, you know, let me give you a couple forms. Now, there's more than one way to do these things because of the nature of sine and cosine, so I'd like you guys to kind of stick to this. That way we're all getting the same answers. Okay, so I'm just going to give you guys some forms to look into. And this should feel similar to inverse trig and some of the other stuff we were working with when we got some of those formulas that we built from scratch. So some of these will sound eerily familiar. So a squared plus x squared m over n. And then this one will be x squared minus a squared m over n. So the substitution we're going to use is x equals a tan. Oops, that's the wrong one. Sine theta. Sorry about this. Got a minus. So sine theta, x equals a tan theta, and x equals a secant theta. The next one is the identity. 1 minus sine squared theta equals cosine squared theta. And then 1 plus tan squared theta equals secant squared theta. And then secant squared theta minus 1 equals tan squared theta. So you kind of manipulate the tan squared theta one. Okay, and then you guys know that the range of theta has some restrictions, right? We talked about this when we did inverse trig. So this guy is negative pi over 2, oops, less than or equal to theta, less than or equal to pi over 2. We talked about that. So basically quadrant 4 to quadrant 1, that's the only thing that sine can be. You guys should have learned this also in pre-calc and trigonometry. This one, same thing. So tangent and sine have similar ranges. And then this one is from 0 to less than theta is less than or equal to pi. Okay, and these don't come up all the time. It's just kind of, that's how I know where I'm drawing my triangle at. And that's why there's not multiple answers. Normally it's just this way. Again, with sine and cosine, since the nature of them are very cyclic, you know, they have a lot of cycle to them. Basically, there are multiple ways to do some of the problems. But like I said, I would prefer this way for grading purposes, just so you guys are all doing it the same way and I don't have to worry about, you know, who's doing it some random way that I've never seen before in my life. Okay, so let's take a look at a problem. Let's go from 0 to 2 of 1 over 4 plus x squared, okay, dx. So let's take a look. Which one does this look like it matches? So if we look here, this is 2 squared plus x squared, right? So this is a and this is x, right? So my a is worth 2, so we should be good on that. So then my substitution is I'm going to say, let's see, which one has a plus sign? Well, it's the tangent, right? Just like with the inverse trig functions, okay? So we're going to use tangent. We're looking at this form right here. So I'm going to say that x equals, let me switch to this. X equals a, and in this case, a is 2, right? I got that from the 4. And then tan theta, okay? And then if I take the derivative of both sides, I get 2 secant squared theta, d theta, right? So I'm going to come over here and I'm going to draw a triangle. You know what? I'm going to hold off on drawing the triangle. I just thought of something. You could go and draw the triangle if you need it. I guess I should do it. I don't want to confuse you guys. So we actually have x over 2 equals tan theta, right? So we know that tangent is SOHCAHTOA, opposite over adjacent. So the opposite is x and the adjacent is 2. So then this becomes the square root of x squared minus 4. Oops, I'm sorry, not minus, x squared plus 4, or 4 plus x squared, which is that guy right there, okay? So that's how that came to be. So now we're going to rewrite this, but I have to change my limits of integration. I have to change my limits of integration because I know that I'm working with x to be 0 and 2, but now I'm going to be working with theta. So if I plug in x to equal 0, that means that 0 is equal to tangent of theta, right? Or 2 tan theta. Divided by 2, divided by 2. You know what, I better write it down here. I'm not going to have room. So we're going to say let x equals 0. So then 0 equals 2 tan theta. So when would tangent of theta equal 0? Well, the tangent of theta would equal 0 when theta is equal to 0, right? Because sine is over sine theta over cosine of theta. Now we come over here and we say let x equal 2, right? So then we have 2 is equal to 2 tan theta, divide both sides by 2. So we have 1 is equal to tan theta. And we know that tangent is equal to 1 when theta is equal to pi over 4, okay? And we know that it's between negative pi fourths and pi fourths. So this is the only option. There are other options that would give you 1, but that would be in quadrant 3. I think, yeah, 5 pi fourths would also give you 1 because you'd have a negative over negative, but we're not allowed to use that because of the restrictions put on this, right? Right here. So we're here. So we have our new limits of integration. So we're going to integrate from 0 to pi over 4. And now we're going to say that dx is worth 2 secant squared theta d theta over the square root of 4 plus, now x we said was 2 tan theta, so this becomes 4 tan squared theta. Now hopefully you guys have seen something. it seems like this number and this number always match, so you can factor it out. That's true. That's kind of one of the things we're looking for. That's why it's very specific how you have to build these. So again, this is a certain format, and it kind of, for us, has to match some form like these three forms. Again, there's other ways to think of it, but these are the three we're really going to focus on. And we have 4 plus 4 tan squared theta. So take a minute and you guys try to clean this problem up and see where you end up. And then unpause the video and I'll go over it with you. All right, so hopefully you guys started with the denominator should be cleaned up a little bit. I can take this 2 out as well. So this becomes secant squared theta d theta all over the square root of 4 times 1 plus tan squared theta. But hopefully you guys are starting to see that this is secant squared theta over, we can take this 2 out, and this will leave me with secant squared, right? Because 1 plus tan squared theta is where secant squared theta, d theta. But this, the 2's cancel. So this is actually equal to the integral from 0 to pi over 4 of secant squared theta over secant theta d theta. Let me erase this real quick. Right, so when I square root that, I just get a plain old secant theta. So now, after all of this, after all this work, we have 0 to pi over 4. Look at the integral we're left with. Secant theta d theta. Right? Now, that's one of the integrals that I gave you in the last section for trig integrals that I told you guys needed to memorize. So this would be the natural log of the absolute value of secant theta plus tan theta from 0 to pi over 4. Now here's the thing. Normally, if we were doing this problem up here, hopefully you guys remembered, when we got to this step right here, when we got to this step, we had to then go and back substitute in what was sine theta worth, right? So that one, we absolutely needed this triangle, right? We needed the triangle, okay? However, here, because we paid the price to switch the limits of integration to pi fourths and 0, we're now working with theta. So we do not actually have to go back and use the triangle. So even though I drew it here, if I needed it, and I have everything set up and I can answer any question you want. However, I don't need it because I converted my limits of integration to match theta. So now I'm left with the natural log of secant pi over 4 plus tan pi over 4 minus the natural log of secant of 0 plus tan of 0. And then this should become, let me see, secant is 1 over cosine. 1 over cosine would be square root 2 over 2 divided, or reciprocal of that, so it would be 2 over the square root of 2. Oops. So the natural log of 2 over the square root of 2 plus 1, right, because the tangent of pi fourths is 1, minus the natural log, secant is 1 over the cosine, so this would be 1 minus the tangent of 0 would be 0. So then this would become natural log of, so 2 over square root 2 plus 1 minus ln of 1, which we know cancels and becomes 0. So this is our official answer. I think in the book, they might try to clean it up to this. They might try to rationalize the denominator, right? So this will become, the 2's will cancel with that, and we'll just be left with square root of 2 plus 1 plus, that's it, plus 0. So that would be our answer, ln natural log of the square root of 2 plus 1. Again, none of these are easy. Look at this problem. All of these problems, even the nice ones, this is what I would consider one of the nice ones. All of these problems are tough, okay? So you really have to take this section seriously. If you are taking this exam online, which we will be this summer, then it'll be a little bit easier because you'll have this table right next to you, and then it's just about choosing which one you want and then making sure you don't mess up on anything, okay? So let's see here. that's it. So there is a few more formulas. So if you use this technique, this is actually where our formulas came from. So remember, we had this a squared plus x squared dx. And if you recall from the arctan, I gave you 1 over a arctan of x over a plus c. So it came from using this technique. And also we had this one, 1 over the square root of a squared minus x squared dx. This one was the sine inverse. Okay, so that's where these two formulas came from. So you don't want to have to build these every time. You definitely want to have those memorized. But if so this way, I think there was a problem we had to do in one of the previous sections where you had to complete the square. So then you could use this arctan stuff. So that is still a possibility, but sometimes they're not given to you in the right format. Your goal is to see if it looks like one of these, and then you can use integration. So if on the exam I ask you to use trig substitution and you don't do it, I'm not going to give you very much credit for the problem, because there are alternate ways that you can still solve these problems. But if I'm testing you on your ability to use trig substitution, then you have to use that technique. Okay. So I have one more I think I can ask you. No, I don't. That one, I already did that one. So that should get you through. We'll try to do one of the harder ones in class together. Those of you that want to stop by our meeting and kind of go over this, we can. But I just wanted to give you guys something to work on with trig sub. One of the harder sections, definitely need to practice some homework, definitely need to ask for help. Just this is a rough one. So just please be sure that you show up to the meetings if you need help. All right, you guys, that's going to do it for this meeting. Thanks for watching, or for this recording. Thanks for watching.